Okay, class, I'll try another video solution here. It says a shallow, the number, chapter 35, number 55. But it says a shallow glass dish is 4 centimeters wide at the bottom and is shown in the figure. So the figure looks something like this. This is maybe the top of the glass, and this is the bottom. And they show that it's 4 centimeters wide here. And they don't really say what its height is. They just label it as h. Okay. It says, when observer I is located as shown, the observer sees the edge of the bottom of the empty dish. Okay, so in order for somebody to see this bottom edge, since the light travels in this straight line, this is our geometric optics, then the observer's eye would need to be somewhere kind of in this location. I hope that kind of looks like an eye. It looks funny with one eye. All right, anyways, but there's the beam of light coming to the observer. Now, with that in mind, watch this. It says when the dish is filled with water, the observer can see the center part. Well, maybe I'll draw in green here this same person at the same location and their ability to see the middle of the dish. Okay, so here's the middle, and I should look, middle bottom, right? The observer sees, when the dish is filled with water, the observer sees, the center of the bottom of the dish. Find the height of the dish. Okay, so the light coming here from the center of the bottom of the dish somehow gets to this observer's eye. And the way it would need to do that is as it comes out here, it then bends away from the normal since it's going from water now into the air. And it would have to follow along this same original path that allowed the observer to see it. And since it's the middle, we could argue that this is 2 centimeters away. Okay, and so we really have 2 sets of beams here, one without water and one with water. Now, obviously, the main part of this chapter is the bending of light or the refraction of light as it leaves from the water into the air. So if I put a normal here, I don't know if I should just throw a new color into the mix, but putting a grid where the light comes, and I'll put the green beam, so the light when it's in the water, it would be then coming in at an angle of what we usually call theta 1, where the light comes in and then bends away from the normal, which we call theta 2. So if I think about this chapter and Snell's law, I would say N1 sine theta 1 is then equal to N2 sine theta 2. And for this particular problem, the N1 is it's starting in water, so 1.33 sine of theta 1 would then equal to going into the air, so that's a 1, and then we have the sine of theta 2. Okay, now, clearly, that's the, I guess I'll call one piece of information. Nothing in there really involves height. However, I think you can see here with angles, something here coming into play. And maybe I'll do this. If I look at sine of theta 1 here, And I guess sine would be the opposite over the hypotenuse. So let me just write, I'm going to change back to red, 1.33. The sine of theta 1 would be the opposite, and so that's the 2 centimeters over the hypotenuse. Now the hypotenuse, I'm going to use Pythagorean's theorem. So it would be the square root of 2 squared plus the h squared. That would be, here's the height, and then here's the horizontal. So there's the hypotenuse. And I guess I've done all my distances in centimeters, so keep that in mind. But see, that's how I'm going to work the h in here, because that's really the question. What is h? Okay, so now over here, sine of theta 2. Well, I'm going to have to do a little geometry. This says sine of theta 2, and so this is outside of the dish. But if you transfer it back inside, this would be this angle, where basically the light just traveled in a straight line when it was empty, and you're looking at the corner. So if you say sine of theta 2 and you focus your attention on here, the opposite would be the full 4 centimeters. And then the hypotenuse would be the 4 squared, and then plus the h squared there. Okay. And maybe I'll do a little canceling before I finish the math. But now it's just a matter of math. We've got one equation here with one unknown, and so find h. So maybe I will start by saying, well, let's square both sides. The numerator, 1.33, when you square it, is 1.7, I'll call it 7, which, of course, on the bottom gives me a 4 plus an h squared. That was the whole point of squaring it, was getting rid of that square root. And then over here, when I square it, that's a 4, and then this would be a 4 squared. Why don't I just write that as 16, and then plus h squared. So when I cross multiply here, I would have 1.77 times the 16, which looks like about a 28.32, so 28.32, and then plus this 1.77h squared. And then over here, when I cross multiply, that 4 times 4 is a 16, and then 4h squared. And now taking the 28.32 and subtracting the 16, we're at 12.32, so 12.32. And then bringing the 1.77h squared over to here would be 4 minus 1.77, and that would be 2.23h squared. And then finally just solving here for h. So I'm going to come up here and take the 1232, I'm going to divide it by the 2.23, and then take the square root of that and get a height of 2.35, and again, I've been using units of centimeter. And there's the answer. Hopefully that helps.